is obvious, right? Because what we have done is we have taken a subgroup which is in between GQ, isotropy at Q, and G. G is our PSL. And we are assuming H is properly contained in G, therefore there are cosets, at least 2 of them. All cosets have the same cardinality, and Xj's are just evaluate all the elements at Q, and then you get some points in the projective space. So this is Xj, and obviously Xj's are non-empty. So I would write here only. Again, I will have to update this file to you, but I will do that. So here, note Xj's are non-empty for every J. That is obvious. Now it's the partition I want to check. What does partition means? That means I have to check that if I take Xj, I don't want to use this color. If I take Xj and intersection Xi and I different from J, and there are elements in, of course, Ij's are, and please don't use the shortcuts because that creates the confusion. These are elements in J, and I want to prove this is this is empty. This is what I am proving. So we'll write the proof. So suppose there is some point in common. Remember, there are points in the projective space. So suppose there is some point in common. So first of all, note that this Xj's, Xi's, this is corresponding to which coset? This is corresponding to GJH. And this is corresponding to the cosets GIH. And these cosets are different because I is different from J. These cosets are numbered like that, and you are taking the distinct cosets. All right. So this statement is equivalent to saying, what does this is equivalent to saying? All right, I will write that later. I don't need it now, so I will write it when I need it. So I am proving this. Suppose there is a point in common. What does that mean? That means if I take these points, one of these will be equal to one of the other. See here, the points in Xj are precisely Gj, H evaluated at Q, and who is varying? H is varying. And the points here are precisely Gi, H prime varying in H prime varying in H only. These are the points here. These are the points here. Suppose they have a point in common. That means these 2 points are equal for some H in H and for some H prime in H. So right here, for there exists H in H prime, H in H, and there exists H in H prime such that this equality. That is the meaning that they do intersect. Agreed? Please, if you don't understand,
yes, sir.
Don't blame the notation. So, what is this equivalent to? This condition is equivalent to, now I will shift. I will shift this on the other side. So I am going to multiply this by Gi inverse. So Gi inverse Gj H prime inverse, and then evaluate this thing at Q. This thing, this equality will tell this equality. Agreed? Because I multiply this by, I clear this, shift it to here, and therefore this will stabilize Q. But this means what? This is equivalent to saying this element is in the stabilizer. So that is Gi inverse G, J, H, H prime belong to IQ. I am calling it IQ, no? No, GQ. This is in GQ. And GQ is contained in H. This is equivalent to saying this, and GQ is contained in H not equal to that is the given. But this, now again I do the same thing. If this is, so in H, therefore, this is equivalent to saying this belongs to H. That means I claim that I multiply by GI. So GIH and GJH. This is an already in H. This guy is already in H. So first of all, this is equivalent. Let me rub this. So this is equivalent to saying, okay, my iPad sometimes GJH equal to GIH. Agreed? Because GI inverse GJ belong to H, therefore I multiply this by GI and then I get this equality. But I do have this because I started with a different I and J. So this is not needed. This is a contradiction. Because they are different cosets. Now is that clear? Roshni, was that your proof?
Yes, sir.
Hello, Roshni.
Yes, sir.
Was it your proof?
Sir, the case where xj, the xj belongs to GIH and xj belongs to GIH. This is what I have proved, that these two are is empty because these two are different, as you gave in the hint.
That is too long explanation for me. I said, was it this your proof? Answer can be yes or no.
So can you repeat again your question?
All right. So that now, Rami, do you agree that we proved that this is the partition?
Yes.
And now I will prove that every G will send Xj to Xi. So what do you have to check? Take any G in G. And then I have to consider what is Gxj. Gxj is precisely apply G to the element. So this J, H evaluated at Q and H is variable. This is precisely G times Xj. And this which cosets it will correspond to? This Xj corresponds to the coset GJH, and therefore this will correspond to the coset GJH. And this coset has to be one of them because we know all the different cosets. These are all distinct cosets. So therefore this has to be one of them. And if this is equal to, so this has to be GIH for some I. And which, how do you decide that? That is, so now therefore this and corresponding to this, there is Xi. So therefore Xi equal to this. So this will correspond to Xi, and therefore we prove this. It's only understanding the definition, nothing else. It's very, very easy. So we have proved that. So therefore we have proved it is a partition Remember, so I will write it again. What we have proved? We have proved that this x's, xj's, j is in j is at least 2, and this is a partition of PV. Right? But now I want to say it's a contradiction. We are looking for a contradiction, no? That is what I said, check that we are getting a contradiction. To what? Double transitivity. Now, see PV, this group G, which is union of these cosets, GJH, this is also disjoint union. This group operates on PV, doubly transitive. That we know beforehand. But now suppose I take P and 2 points I will choose. See the cardinalities of x's, xj's is at least 2. So if I choose P prime and Q prime appropriately, so what can I choose? Can somebody tell me? See, suppose I choose this P and P prime in a different, this is in a different subsets in the partition, and these are in the same. Then the only chance that G will map both of them to these both of them only when if they either belong to the same set in the partition. Otherwise, any G will carry this P to somewhere else and P prime to somewhere else. And do you understand? See, suppose I choose like this. The partition has 2 sets, let us say, like this. And this is another one. Now I choose both of them here, Q and Q prime. Here I choose only one P, and another one I choose, or here I choose P prime. Suppose I do that. And then what G I can choose? The G, if I take any G, either this will all go with this, or this has to go to somewhere else also. And it will not go partwise. All these guys have the same cardinality. Xi, all these guys have the same cardinality. Therefore, it cannot happen the double transitiveness. I hope it is clear what I'm saying. If not, please raise. Otherwise, I will continue the proof. And this file I will have to send you an update. Yes, please. Ramir.
It's clear. That's what I said.
All right. Now,
sir, can you please repeat this?
Shall I repeat this?
Yes, sir.
Right.
Last part.
See, note, Purnashri, all these subsets in the partition. Who asked me the, please check again? Tithi.
Tithi,
Yes.
Okay. So all these partition, these X's, they have all the same elements. Anyway, all that we know is any element in G will map one of the subset in the partition to the other subset. And because it is a group action, it will be a bijective only. So anyway, so suppose I choose, what do you want? We have given that G operate doubly transitive, means for 2 distinct points, the images, I can choose G, which will map P to Q and P prime to Q prime. I can choose the same, I can choose one G in G, such that this. Now, if I have chosen P in one of the partition set, and the other partition I choose 3 points. And now I want, if I want this P to go to Q, P to go to Q, and this P prime go to Q prime. Now, how can this happen? Because this is G. In the G, there is no G. The other points will go to, of course, these points here somewhere. But the P prime, how can it come by? How can P prime will go to Q prime? That will not happen. Because of this configuration, what we have, it's very neatly packed. All right, you can still write down formal proof for this. So I just gave you the idea, but you can write down formal proof. You check that in such a configuration, there won't be any G which will map P to P prime. And no, P to Q and P prime to Q prime. There won't be any G which will map this, because if you want G, if you want some element of G mapping P prime to Q prime, then it will, this subset will go somewhere else. Right, so that is the problem. All right, so again, you can write the proof more precisely, and some of you already have written, I was told. So you can discuss with those guys. If not, you can again write it. I will discuss again in the tutorials. All right, so I am getting again delayed by the. So now today, what I am going to do? I am going to study. I am preparing the next step now. See, what are the steps we prepared? We started with a subgroup which is non-trivial, and then we proved that normal subgroup, if it is not G, it operates transitively on P. That we checked. Then we proved that G operate on P with doubly transitive. Then we checked that the isotropy at any point Q is a maximal subgroup. Right? This is what we were checking for that. Now I want to, the next one, I want to study little bit linear algebra. This comes under now basic linear algebra, but probably you have not studied in this language, and I would like also to start from the red exercise. I think you have not looked at it, namely the pseudo reflections. I want to study the pseudo reflection more precisely and the group generated by that. And this I don't know. This is a very easy geometry, so I will also do geometry, but I will do more algebraic part today, so that you are more comfortable. All right. So I am recalling a definition from exercise 221. So it says, when do you call I will also keep my calculation if I need it handy. All right. So an automorphism is called a pseudo reflection if it fixes hyperplane pointwise. That precisely means if you look at the f minus idv, f minus idv is also mapped from V to V. And f is fixing pointwise means fx equal to, so this is what by definition it is all those x in V such that f of x equal to x. And this is same thing as the kernel of f minus idv. And we are assuming it is a pseudo reflection. By definition, it means the fixed point set is a hyperplane in V. Hyperplane means one dimension less. Line in a plane is a hyperplane. Plane in the space is a hyperplane. So these are the hyperplanes. But now I don't like this H notation in the hyperplane because that will get again subgroup and so on. So I will think even in that exercise 2.1, I have thought it more differently, more geometric way. So what will I think? So remember, hyperplanes, this you must be studying in your linear algebra course. Hyperplanes in V, they are one-to-one correspondence with the linear forms. V star. V star is Ohm, K, Vk. The elements of these are called linear forms or linear functionals. In functional analysis, they use the word linear functionals. I will use the linear forms. And hyperplane H will correspond uniquely to a non-zero linear form phi. Phi is a linear form. And what is the association? If you have a linear form, you take the kernel of that. And that is H. If you have a linear form, non-zero, that means it is surjective, that means rank 1, and therefore the kernel will have dimension 1 less. Rank of phi is 1 because it is non-zero, and therefore dimension of the kernel, because rank nullity theorem, that will be 1 less. It will be n minus 1, where n is the dimension of U. N is the dimension of U. So I will think hyperplane as linear form. Therefore, this is my linear. This is the linear form. This rank. So kernel is here. Kernel of f minus id is, we are assuming it is hyperplane. Therefore, also we know that the image of f minus id v, this will be one dimensional, and it will be generated by some element y, where y is non-zero. Because kernel, this is n minus 1 dimensional, therefore image will have dimension 1. Again, rank nullity theorem. This was the most important, first trivial but most important theorem one learns in the basic linear algebra. Rank plus dimension of the kernel equal to the dimension of the ambient space. All right, so, and it is generated by y, some y. And this y is not unique. There are many elements which generate y. But what is that y in terms of this phi? That is that phi of y is non-zero. Not non-zero, sorry. Phi is a linear form. So phi, somebody definitely goes to 1. And that's all. I will write it more precisely when I need it. Now I want to describe all these pseudo reflections with this property where hyperplane is fixed. All right. Is that clear? Anybody has a question?
It is clear.
Ramir, this is very, very important. What I said here
Yes,
now,
yes.
and I will use it again and again. The whole discussion will depend on this. This notation also. And notation is not complicated. All right.
Yes.
So what do I do? Yes, Ramveer. Or who want to ask any question? Don't hesitate.
No question, sir. No question from.
All right. So now I know that the image is generated by y and these points are fixed. Therefore, what can I write fx? I will write fx minus x or equal to x plus phi x times y. Do you agree? Where this phi x is in k. And do you agree to this? And this equation is true for every x. This is very important. Because look at this, if I shift this to the other side, that means this is in the image. and the image is generated by y. Therefore, it is some scalar multiple of y, and that scalar multiple I call it phi x. Is that clear?
Yes, sir.
Yes, sir.
This is very, very important equation. And all the time, the calculation will be done with this. This linear form is connected like this. All right, now in this first remark I say, first one, note that y and y is in k. Y is in k and y is non-zero actually. Why? If y is 0, what happens? Let us see. If y is 0, for every x, f of x will be equal to x. That means the whole v will fixing this. That's not the case. Because it is a hyperplane that is given to you. So therefore, whole v is not fixed under f. So that y is non-zero. And that phi is a linear form then. Phi is in v star. And phi cannot be 0. Because if it is 0, then again this x, phi x will be 0 for every x. And then again the same problem. All right. And this phi in fact will correspond to that hyperplane fixed points. It's clear. Because when will phi x will be 0? Precisely when it is a fixed point. So this means x belong to the fixed points if and only if phi x is 0. That is the meaning that these correspond to each other. All right?
Sir, y is a vector, right?
Sorry?
Y is a vector, na?
Your voice is pretty poor, Nashri.
Okay.
What,
Now
what is it?
is this? Sir, I am asking that whether y is a vector or not.
Why? Oh, sorry. Thank you. Y is a vector. Of course, thank you. So, the y is a non-zero vector in V and phi is a non-zero linear form in V, and we have this equation for any pseudo reflection. That's what we have checked. And not only that, I want to write one more extra comment that y and phi are uniquely determined up to scalar multiplication. This I want you to check. So I will write here, you should check this. What does that mean? That means if there is another y, there is another phi which also satisfies this equation, such an equation, then that y will be a scalar multiple of the other y. And similarly the linear form. That is very, very simple to check. Of course, all these things, many books will do all this by doing a matrices, and that is a horrendous thing. But somehow many people feel happy with the coordinates. But they actually it takes away a lot of energy. So if you conserve your energy for good things. All right, so this is, I will not check. If there is a trouble, we will check in the tutorials. All right, so that is the first remark. All right, now comes a definition. So definition. Also, what is the definition? So F is the same notation. This F, so F in GLV be a pseudo reflection. And this F I am going to denote by this pair. Phi Y. This is the notation I am going to adopt for the. So given a pair where this is a non-zero, so this is where this is a non-zero linear form. This is a pair in V star cross V. This phi is non-zero, Y is also non-zero. Given this, I can get back my F, namely this formula, that formula. F of X equal to X plus phi X times Y. You see, this equation is the one which will make a lot of calculation very easy. You will see that. So when do you call it? So that was the exercise I was trying to write here. Pseudo reflection has this property rank is 1. I was drawing these pictures and I was trying to do some. I wanted to write more, but I was tired and I also didn't have hope that any one of you will read it. Therefore, I wanted to conserve my energy, so I left it. But I realized I have to do little bit. I will not do more in that affine spaces, but at least in a vector spaces I will do it. All right. So now, one F is called transvection. Why do I write capital here? This should be small. Or some books you will see, they will also call shearing. If P of Y is 0. Which is equivalent to saying this Y will belong to the fix FV. See, phi Y is 0, so Fy equal to Y, phi Y is 0, so Fy equal to Y. So it is a fixed point. So then we call it a shearing. If phi Y is non-zero, if F is called a dilatation, if phi Y is non-zero. And one more comment I forgot to write it here. These are uniquely determined up to scalar multiplication, and phi Y is uniquely determined. Phi Y is what? Phi Y is a scalar now. Remember, phi Y is a scalar. This scalar is uniquely determined by F. And this scalar, therefore, I will denote this scalar phi Y. I will denote lambda F. This is an element in K. All right, that is also very easy to check. Just remember this equation and noting that phi is a non-zero linear form, Y is a non-zero vector. From there, all these three checking should be done immediately. No other thing. Now this is called a dilatation, and this, therefore, this is lambda. No, this is lambda of F. And in this case, this is lambda of F. So lambda f is 0 in this case, lambda f is not 0 in this case. And then I want to draw the picture. That is where I explained the picture draw, and the picture will shed a light on why it is called a shearing. Shearing, you know, shearing means scissor. imagine a scissor, that is called shearing. So I tried to draw the picture here. Obviously, I didn't want to waste my time during the lecture, so I drew it. I did my homework. So this is a shearing. Stare at it sometime and tell me whether it is okay. So this means that vector y is in the hyperplane. This big shaded thing is a hyperplane for me. And this is, and then if I take a P point outside this hyperplane and apply F, I will get a point outside that vector. Not only that, that line will be parallel to this line. So that line will be parallel to that hyperplane. That means this line will not intersect with the hyperplane. If I take another pair of points, this point down, this line will also not intersect, but the direction has changed in this. You see here, that is why it is called scissor. You see these arrows. So if I press it here, that will expand. If I press there, so this is exactly like a shear. Exactly like a, what do you call it, katri or scissor. So stare at this picture and remember here, as I said, I have identified this phi, f, phi, this. Now I will write down the matrix of this soon. I will choose a basis and I will write down the matrix of this. All right. This is one. Now the other picture, dilatation. You have done dilatation also in exercises. That is like a magnification. And this lambda is a magnification factor. And this lambda can either be positive or negative. And now you will say K is not real number, but still, these two pictures will explain that. So the dilatation factor is the factor with this. If you have a line and then this get reflected. So therefore these pictures are very self-explanatory. I spend a lot of time to write only the necessary information in this picture. And all necessary information is there. So I want you to stare these pictures when you go back today and tell me it is okay. And picture doesn't matter now. Our algebraic description is there. But picture will help you to imagine. All right, so that is a shearing and a dilatation. And now I will write the corresponding matrices. I will choose the right basis so that their matrices are better. See, I don't want to take arbitrary basis. If I take arbitrary basis, then obviously the matrix will have ugly form. So the calculation with the matrix will be troublesome. So I want to find a good basis so that the matrices look better. Better means what? There are many zeros. And then you will see what is there. All right. So now the next observation I want to make. So I will write it as a proposition. And what do I want to study? Okay, I will tell you beforehand. So remember, why did I write this notation? I don't want to study dilatations now. I will concentrate on transvections. And they are this. Either F, I will think either F or this. Pairs with this equation. Of course, I have written that equation on the top here. And this is true for all x. This is for all x in V. And phi y is 0. Phi y is 0. That is what we have written. Phi y is 0. And you are denoting this pair. So I am going to fix. So what is the future? What I am up to is the following. What I want to do is we want to study y is given vector. Y is non-zero vector. This is fixed. And I want to study transvections Ty. Not Ty. Let me call it therefore not Ty. This one. Phi and Y, where phi is linear form and phi is non-zero, and all such things. And this I will, this depends on Y. Y is fixed. And here also we know that because transvections, this notation says phi of Y is 0. And this I want to write it Ty. And obviously the identity is not there. See, this transaction will not contain identity. So I union with identity map. Therefore, I got hold of this Ty is what? Ty is a subset of GLV. And what do I want to do with this subset? I will prove that this is an abelian subgroup. That is my aim right now. All right. That is why I want to study this transaction. That is our aim. And this is very closely related to that isotropy. Because ultimately we want to get a contradiction that isotropy is a maximal subgroup. No? So I want to do something with that isotropy. But before that I want to study this. And this is purely linear algebra. This is nothing more. All right, so I am up to that. So therefore the first proposition I want to prove is the following. Let F in GLV be a pseudo reflection. And therefore that fix FV I am going to denote by phi. Phi is in V star and phi is non-zero, and there is a Y. There is a non-zero Y in V with this equation. Fx equal to x plus phi x times Y. And this is true for every x in there. This is a pseudo reflection. If you again, you go and stare those pictures. All right. First thing, I want to write a good matrix for the this linear map. And I want to choose a good basis so that the matrix is good looking. So F, if F, assume that, suppose that F is a transaction. That is phi of Y 0. Okay, then I want to say that all eigenvectors of F, EIG, F, these are eigenvectors of F. They are all contained in H. With I will write here with eigenvalues 1. All of them are lying in the hyperplane only. So it's obvious if you have a eigenvalue 1 eigenvector, what does that mean? That means that is f of x equal to x. This x is an eigenvalue, x is non-zero, and then x is called eigenvector corresponding to the eigenvalue 1. Right? And all of them are obviously in the fixed point set of V, F. That is obvious. But I said there is no other eigenvalue. There is no other eigenvector. There is no other eigenvector other than the fixed points. That one has to prove. All right. So that I am not going to prove. This prove. This is an easy statement. What does that mean? That means you have to prove that if f of x equal to some a times x, x is non-zero, and a is in K, then the only possibility is a equal to 1. So this should imply a equal to 1. That is very easy checking for you. You should do that. So this is what you have to do. All right, so this is not difficult, but then what do I say? All right, then I say the matrix, there exists. This is the more interesting statement for me. There exists a basis V1, V2, Vn. So the basis I am denoting by V here, V underline of V, such that the matrix M, V, V, F is what? Is B1, 2, 1. I hope you have not forgotten this notation. B1, 2, that is at 1 position 1, and everywhere else it is 0 other than the diagonal, which is 1, 1, 1, 1. So this matrix is 1 position 1 and diagonal 1, and everywhere else it is 0. The entries which I have not done, they are all 0. So that is the matrix. This is the elementary matrix. Remember, I don't remember which lecture, but that is the matrix. So that was one. And I will write down for the dilation also, so that you will not feel that what happens to the dilation. So now the second, suppose that F is a dilatation, that is phi of y is non-zero. Then you can find, then there exists a basis let me write the short V of V such that the matrix MV is, which is the matrix. I will write down the matrix. So that matrix is the diagonal matrix. So DIAG, that is the notation. What comes here is lambda plus 1, 1, 1. So that is this matrix. lambda plus 1, 1, 1 and 0. This is it. If you have forgotten what is lambda is that value. Here, lambda is that value. So remember, lambda is phi of 1, which is a non-zero element by our assumption. All right, so I will tell you the proof of 1, proof of 2 is similar, that you can do it. All right, so proof of Ponashri, all these statements which I am not proving that they should do it in the tutorials. I am not making an extra sheet.
Okay,
all right,
sir. Okay, sir.
All right. So first the proof of 1. So proof 1. What is given? We have given non-zero y vector, non-zero linear form, and phi y is 0. This is lambda. This is lambda of f. So lambda of f is lambda I denoted. And my f is this. This notation, phi y. What does that mean? That means this equation, f of x equal to x plus phi x times 1. And this is for every x in V. This is the meaning of this notation. All right, now we want to find a good basis. So what do I know? Now phi y is in, so this condition means that y is in the fixed plane. Y is in this hyperplane. And this is n minus 1 dimensional. So I can definitely take this y is a non-zero vector there, one of them. I will extend that to a basis of the fixed point set. So that means what am I doing? Y, I call it V2, V3, up to Vn. This is a basis of fixed point set. All right. Then I want to choose one more vector along with this. All right. I know this linear form is non-zero. So I can definitely choose. So I will here choose x in V such that phi x is 1 actually. It's a linear form, non-zero linear form, so it should be surjective. So 1 is in the image, so I will choose x so that x goes to 1. So right here, this we can do it because phi star is non-zero. And take that x and look at f of x. What is f of x? That is x plus phi x y. That box equation. Whole day and night you dream about this box equation. That every information about that linear map or transvection is coded there, or even dilatation. So this is x plus 1. All right. Now I take that x as v. I will add here. So now consider v1 equal to x, v2 is y, etc., etc. Vn. This I say this is a basis of V. That clear? because this f of x is, so what can happen? I want to just show that this x along with x and y are linearly independent, no? Yes or no? Can you check that or should I check that? Hello, Rahul.
Sir, y is not in.
Sorry?
So they're linearly independent, right? They're linearly independent. Y is not in span of x.
Yes. They are linearly independent, right? Because phi of x is non-zero. So it's a basis. So I want to compute a matrix of F with respect to this basis. So M, V, V, F. How do you write a matrix of a linear map with respect to a basis? The first column is the image of the first basis vector. So if I want to write the first column, it will have to take the image of x, but that is x plus 1. And y is the next vector in the basis. So this will be 1, 1. And then zeros. Y, the next vector is y. Where do y go? Y go under f. Where do y go under f?
So y plus phi of y times y.
Sorry?
So when
F
we
of y
evaluate,
is y because y is fixed. No. F of y is y. So this equation
yes,
will
sir.
tell y is y. So it is 0, 1, 0, 0. Note here f of y is y. From this equation, specialize the x equal to y. F phi y is 0. So this will go away. So f of y is y. So the next column is 0, 1, 0. And the remaining guys are fixed. So therefore they will be diagonal matrix. Remaining guys are 0. So isn't this matrix as B1, 2, 1? See, this entry is non-zero. This is 1, 2 entry. 1, 2 or 2, 1. Is it correct?
Sir, it should be 2, 1.
2, 1, 2, 1, sorry. Here also in the statement it should be also 2, 1. This is 2, 1. All right, now we finish this proof. Obviously, 2 I am not proving. 2 is more simpler. Don't know. All right. 2 is more simpler, I guess. So, and anyway, 2 I am not going to use it. All right, now I come back to what I said. In fact, I want to write one statement here which you need, which you prove it. So this I will again write in the red one so that it needs to be proved. But you have all the ingredients to prove it. What does why I want to say that? That I want to say that these matrices B, I, J, A, where I not equal to J and A is a scalar and a non-zero scalar. So this is that elementary matrix which you got it by adding a multiple of jth row to the ith row. All right. So that is that elementary matrix. And on the other hand, we have this B21 matrix. This, I say they are conjugates. Conjugates in GLV. What does that mean? That means all these once you get this matrix, all these matrices, you obtain them as a conjugates of this. So if you say this is, if I will write better to write instead of matrices, better to write in the linear map. So F. This F is a transvection that we just got it. And this, if you call that Fij, this and these are conjugates. That means Fij equal to some G inverse, where G is in GLV. That is what the statement I am saying. So therefore, this is need to be proved. So you prove it. So why did I write matrices? Because you choose a basis so that matrix of this and matrix of this, they are this, and that will prove they are conjugate. Similar matrices are conjugates to each other. All right. So this needs to be discussed in the tutorial session. All right. Now the next one. So don't forget our aim. What is our aim? Our aim is to study the group of transvections and where this y is fixed. And I want to show that is an abelian group. So I should write some formula. So next I am writing a proposition which will enable you to see what is the group structure there. All right. So next proposition. And this proposition is so very easy that you will see. You don't have to prove many things. It is so obvious. So what is it? Now the notation is we are denoting F in GLV. We are denoting this F by phi y. Phi is a non-zero linear form and y is a non-zero vector and phi y is 0. Yes? Anybody want to ask any question? There was somebody's mic was on. Anyway, so these are the transvections, and that is what we want to study. See, that is what I wrote it. That is what I want to study all these transvections together. And my aim is to prove that it is a abelian group. And it's a subgroup of GL. So I should have a formula for the multiplication, because the group structure is multiplication here, but I want to say it's abelian group. So I should prove accordingly. So that means I should tell you what are the formulas with these pairs. And I am writing general now. Not necessarily with this condition, but in general. So this is just to remember. This is just to remember. But I am writing it together for maybe dilatation and transvection together. So where F is, we are denoting F by this. So the number one, point number one there. How do I compose such two maps? That means phi y compose phi prime y prime. You understood this notation? This means that pseudo reflection which is defined by fx equal to x plus phi y times y. This one is that reflection, that formula in the box. This formula. This formula is that notation. That's what I said. These are all pseudo reflections. So we are writing formulas for the pseudo reflections. And what is this? This should be again pseudo reflection. That is, I will tell you the formula. So first I am writing it for first component same. This is phi comma y plus y. Second, now I vary the first one. So phi y compose phi prime y. This is same as phi plus phi prime comma y. The third one, now I write for both. Where are they equal? Phi y equal to phi prime y prime if and only if phi prime is a scalar multiple of phi and the same scalar multiple, and y prime will be the same scalar multiple of y, where alpha is an element in K cross, non-zero element in K cross. Fourth, if G is in GLV, then G conjugacy class of this. These are the conjugates. These are the conjugates of phi y in GLV. This is same as phi G inverse comma GY. We have understood what is to be proved. So for example, as a sample, I will prove one of them and then you will see how easy it is. And remaining ones, we do it in the exercises. So proof. I will prove sample proof. Sample, I will give sample proof of three and this side. That means assuming this, I want to prove this. All right. All right. What is given now? What? Oh, sorry. What is given? These pairs are equal. That is given. But what are these pair at V? So take any V in V. Take any V in V. And this equality means what? I am writing down for every V in V. That means so phi of V. So that means V plus phi of V times Y is equal to V plus phi prime V Y prime. Agreed? Ramveer.
Yes, sir.
Do you agree to this equality? This equality means this equality, I say.
Yes, we just putting, yeah, we are just.
I'm just evaluating this left hand side
Yes.
at V and that is this, and this left hand side at V, it is this. That is the definition
Yes,
of that.
sir, yeah.
Don't tell me that it's very complicated. So this is not phi here. There was a writing mistake here. This is y. See what does this fy means? Fx equal to x phi xy. That is the notation. Right? So when I evaluate this at V, I have to evaluate phi, I have to add to V, I have to add phi of V times y. That is what I have written. That is the left hand side, and this is the right hand side. That is given to us, and I want to prove this. I want to prove that phi prime is a scalar multiple of phi and y prime is the same scalar multiple of y. Roshni, is it clear? Hello, Roshni.
Yes, sir. Yes, sir.
Is it clear?
Yes, sir.
Notation is not complicated. All right, so that is given to us for every V. So that means I can cancel V. We are in an additive group. So I will cancel this. So I have given this equality. So now from this equality and this phi and phi prime, they are linear forms. They are non-zero linear forms. Remember, in this all this notation, all y prime, phi prime, they are all non-zero. So they are non-zero linear forms. So therefore, there will be V where all these are not zero. So there will exist, for example, there will exist some V so that this, for example, this is non-zero. This one will be non-zero for some V. And for that V, I am going to shift this to the other side. So you choose V with phi of V is non-zero. So there exists V with this, and then I'm going to shift this to the other side. So I'll get Y equal to phi V. This is a scalar, remember, it's not a vector. This inverse times phi prime V Y prime. And this is the scalar I got alpha. So therefore, I got Y prime, Y equal to, but I wrote here Y. Okay, so that I have to shift this alpha is non-zero, so I will have to shift it to the other side. All right, that is my alpha. Now I want to prove that this phi prime is a scalar multiple of phi. All right, so what do I do? I want to prove. So to prove, I will write here, to prove phi prime equal to alpha phi. What do I have to prove? That is, for all u in V, phi prime u equal to alpha times phi u. This is what I want to do. All right, now let me see when it is zero. So note phi of u is zero if and only if this is zero, then this will also be zero. Because this alpha is a scalar. Because if you want an explanation, y prime both are non-zero. That is from this equation also you can see. Y prime are zero, so this is coefficient is zero if and only this coefficient is zero. That. And therefore I can now read y. Okay, so y will be equal to phi u inverse phi prime u times y prime. And this is now non-zero. This is my alpha, this is non-zero. See, this alpha, this is not good because I don't know, it may. So this is alpha. Of course, it is the same. And this doesn't depend on V. V is non-zero, then it is, because of this equation, because of this. And that's it. So I said everything is finished. You check that I have proved correctly. And the idea is very clear. Don't want to waste more time. Idea is very clear, very self-explanatory. You just sit down and apply your definitions correctly, and you will see. Shall I continue? All right. So now, therefore, what happened? What is the structure?
Sir,
Yes, please.
Sir, since it is, I mean, there is only 1 minute to 6. So,
Correct. Fine.
sir, I want to ask you something that what should I do in tomorrow's tutorial? Because I have only one submission.
What is your, see, if they are not submitting, that means they are not interested in doing exercises. And
So
we
shall
can
I go to fourth set?
Huh?
Shall I go to the fourth set? Means then in that case I have to explain, because the person who has submitted, he has submitted only one part. I mean, just one question.
So, okay, you whoever has submitted, you discuss that and